Hello, welcome back to our continuing discussions on continuous random variables and their probability distribution functions. This is Dr. Leslie Ann Asmus, and in this recording session, we're going to go ahead and turn our attention to the exponential distribution, random variables that follow an exponential distribution. Intuitively, what we looked at in the last session were random variables that follow probability distribution functions that were uniform. And what that meant is that the probability that the random variable would take a value in a subinterval of the same length would stay the same regardless of where that subinterval was between A and B. So we said, okay, we had one example where we said, okay, what's the probability of delivery time was uniform between 1 and 5 days. So the probability that the random variable X would fall between 1 and 3 days was the same as the probability that the random variable would fall between 3 and 5 days. That certainly applies to some situations and different places. You know, it's used in different ways. But clearly it's not going to hold for a lot of situations. So we next introduce the exponential distribution, where we say the probability over subintervals of the same length decreases as the subintervals move farther and farther to the right. So you see the picture, the bottom picture there of an exponential probability distribution function. We see that if we looked and said, okay, a subinterval of length 2 in this distribution, you did the whole integration of underneath of the area under this curve here, as the random variable value gets larger and larger, of course, those probabilities that it falls in subintervals of the same length get smaller and smaller. Some examples of random variables that follow this type of distribution might be the probability of a call until the next call comes in. If you're talking about an operator or a call center, what's the probability associated with the time before the next call comes in? So you would hope that time between, or you know, if calls are coming fairly frequently, the time between the next call, as the time gets quite large, you would expect that probability associated with that to go down. So let's look at the, given an interval S, subintervals of length D are less likely to contain a value for X as the interval moves to the right, as it gets larger and larger. The subinterval, the values looked at are getting larger and larger. And we see that the exponential distribution with parameters theta, where theta is non-negative, if the PDF of X is defined as you see here, probability that X is equal to 1 over theta, e to the minus X over theta for X greater than or equal to 0 and 0 otherwise. The mean for exponential distribution, for an exponential distribution, is simply theta, and the variance associated with it is theta squared. So the mean and the standard deviation are both the value, whatever theta is given to you. Okay, so the general form of a cumulative distribution function, recall that that was simply the integration of P of X, or P of T in this case, rather, so integrating T from minus infinity to X to find f of X. If you were to do that using P of T defined in the previous slide as this 1 over theta, e to the minus X over theta, if you did that integration, you would find that your cumulative distribution for values of X greater than or equal to 0 is 1 minus e to the minus X over theta. So again, you could use your calculus to go and show the mathematical proof of this is the cumulative distribution function for an exponential random variable, or a random variable that follows an exponential distribution. I'm going to just be giving it to you, and unless you're curious to go prove that out, I'm happy to leave it at that you just use that as kind of your working formula. Okay, so a sugar refinery, here's an example of a exponential distribution. Sugar refinery has 3 processing plants, all of which receive raw sugar in bulk. The amount of sugar that one plant can process in a day can be modeled as having an exponential distribution with a mean of 4 measurements in tons for each of the 3 plants. If the plants operate independently, find the probability that exactly 2 of the 3 plants will process more than 4 tons on a given day. Okay, so follows an exponential distribution with a mean of 4 tons. So we first recall that for an exponential, well, I'm kind of just said that here. For the exponential distribution, the mean, the expected value, is always equal to the rate that you're given in this case, which is 4. Probability that any given plant will process more than 4 tons on a given day is the probability that the random variable will be greater than 4, which is equal to 1 minus probability the processing will be less than or equal to 4. The random variable will be less than or equal to 4. And that is just plugging in from the previous slide, 1 minus, and now here's probability that x is less than or equal to 4 is simply equal to 1 minus e to the minus 4 theta divided by 4, or rather, minus 4, the top 4 is for the x that we're interested in, and the bottom is the theta. So that's just e to the minus 1, or 0.37. So that's the probability that any one plant would process more than 4 tons in a given day. And so this is actually pulling in a couple of things. Suppose that's the given probability of success. You switch the out. Assuming the 3 plants operate independently, the problem is to find the probability of 2 successes in 3 trials, where the probability of success is 0.37. So this should ring a bell to you about something that we did previously with the discrete random variables. So if you have x being the continuous random variable regarding the processing in tons of a particular plant, and it follows an exponential distribution, you could have y, a separate random variable, noting how many successes, how many plants out of the 3 process more than 4 tons in a given day. So probability exactly 2 plants use more than 4 tons or process more than 4 tons is a binomial distribution. Probability of success P is equal to 0.37. So 3 plants, exactly 2 process more than 4 tons. 3 choose 2, 0.37. The 2 that are succeeding, square that, times the 1 that is not, and that's the 0.63. So that's 1 minus 0.37. And so you get a probability of 0.26 that exactly 2 of the 3 plants will process more than 4 tons on a given day. Learning checkpoint. Magnitudes of earthquakes recorded in a region of North America can be modeled by an exponential distribution with a mean of 2.4 as measured on the Richter scale. Find the probabilities that the next earthquake to strike the region will have the following characteristics. First, find the probability that it will exceed 3.0 on the Richter scale. Find the probability that it will fall between 2 and 3.0 on the Richter scale. So again, the solution to this is also on the blackboard, but go ahead and give that a try using what you know about the exponential distribution, using these definitions. Okay, this is a little bit of a side thing that